Okay, let's unpack this. The digital world, it's just, it's vast, isn't it? Feels like you're trying to navigate this incredibly dense kind of opaque forest sometimes.
It really can seem that way.
But here's the secret. Maybe. The whole physical foundation of our modern IT infrastructure, this digital ecosystem, it's actually built on just 10 core categories of devices, just 10.
That's right. When you break it down, there's a structure there.
So our mission today, it's pretty straightforward. We're not just going to list them off. No, we're giving you the architectural deep dive, the shortcut really, to understanding the precise function of every single device.
Yeah.
From like the phone in your pocket to those critical servers and embedded monitors you probably never even see.
Exactly. We're looking at the why behind the design.
We've pulled together a bunch of detailed spec lists and some foundational IT system design documents.
Yeah, and the real insight, I think, comes when you see the relationship between these 10 categories. It's totally an interconnected ecosystem. The goal is to get beyond just knowing what a PC does and understand, well, why does it need a file server, and how do both of them end up relying on something like a router?
Exactly. This is your guide to that physical infrastructure. And those AHA moments, they really click when you realize the same basic functional ideas apply, whether you're talking about a giant data center or, your own smart home network.
Scales up and down.
So we're starting at the most familiar point, right?
Yeah.
The user interface, what we're calling the personal productivity stack.
Right. This is the front line. These are the devices you, the user, actually touch and interact with to get work done or talk to people or create things.
And first up, the heavyweight champion, personal computers, PCs. That's desktops and laptops. Now, we know their general purpose, but architecturally speaking, why are they still sort of the cornerstone of productivity?
Well, I think it comes down to two critical things. They have really robust local processing power, right? And crucially, the user generally gets to choose or heavily customize the operating system.
Yep.
Unlike, say, a specialized terminal, a PC gives the end user the most flexibility and control. But that's also a major architectural point to consider.
Oh, so?
That versatility means they're the main points of exposure to the network. They're the critical endpoint where all the software lives, where configurations are set, and, let's be honest, where most security vulnerabilities tend to pop up.
Ah, okay. So their biggest strength, that flexibility, is also kind of their weakness from an architectural view. They need a lot of careful management because they're so customizable.
Precisely. They're managing their own software. They're constantly connecting to peripherals, local networks, the cloud. It's a lot. They're definitely high maintenance, but also high reward, real workhorses.
Makes sense. Okay, moving on. Often right next to that PC, you've got category number 2, the multifunctional device, or MFD.
Ah, yes, the MFD.
These combine printing, scanning, copying, and sometimes, believe it or not, faxing, though, faxing must be fading fast now.
It certainly is fading, yeah. But the MFD's architectural value is really about integration and giving everyone central access. Saves space, obviously.
Right.
But more importantly, modern MFDs are really essential network devices now. They're shifting away from just being a local printer plugged into one computer. Now they're network document handlers. They can scan straight to cloud services or network drives, that kind of thing.
Okay, I have to ask then. As the host, I'm genuinely curious. With this big push towards paperless offices, how long do you think until the MFD is, functionally obsolete, replaced completely by mobile scanning and cloud storage?
That's a really sharp question. And yeah, the MFD is definitely feeling the pressure.
Right.
But I think its resilience comes from handling high-volume, enterprise-level printing, and also really rapid document digitization. Mobile devices, they still kind of struggle to match that speed and efficiency, especially at scale. Plus, regulated industries, they often still require paper documentation trails. So MFDs remain pretty crucial there.
Fascinating. Okay. So now we step away from the fixed desk, the office setup, and into the pocket. Category number 3, mobile devices, smartphones and tablets. Beyond just being portable, what's their architectural significance in the bigger IT picture?
Well, they probably represent the single biggest challenge to traditional IT infrastructure.
Really? Why that?
Mostly because of the sheer volume of devices and also the whole bring your own device or BYOD trend.
BYOD.
These things are ultra portable, sure, but they're also incredibly powerful little microcomputers, and they generate massive amounts of data, often intermittently. They're constantly asking for authentication, for synchronization,
Right.
and that puts just enormous strain on the back-end servers and especially the wireless access points.
Okay, so the mobile device is this tiny, powerful data generator, which actually makes the next section we're going to, the central nervous system, absolutely critical for handling that scale.
That's a perfect transition. Exactly. We're leaving the personal stuff now and going into the devices that actually power and manage the whole digital operation. Right. And here's where it gets really interesting, I think. We need to sort of dissect the differences between the three main essential types of servers.
Okay, let's start with the one most people probably get intuitively, the file server. What's its specialized role? Why can't a regular PC handle that job, especially at scale?
Okay, so the file server's job is specialization, specifically in storage and retrieval. But it's heavily focused on security, controlling access, and resilience, making sure the data stays safe and available.
Right.
See, a PC is really designed for one person using it at a time, a file server. It's built for potentially hundreds, even thousands of users hitting it concurrently and securely. It manages complex permissions, it centralizes version control for documents, and crucially, it handles continuous data redundancy and backup protocols, stuff that would just cripple a standard desktop computer.
Got it. So it's not just like a big hard drive sitting in a corner. It's more like a dedicated librarian, super focused on safety and availability for everyone.
That's a great analogy. Exactly. That focus on centralization and resilience, that's key. Okay, next up, the application server.
Okay.
Now, this is a bit of a functional leap. These servers don't just store files. They run and manage the actual software. They deliver services to users across the network.
So if the file server is the librarian, is the application server more like the central processing plant? And how does using one change what you need from the end user's PC? Does it make the PC less important?
It creates a really fundamental architectural trade-off. Using an application server lets you adopt what's called a thin client model.
Thin client.
Yeah, it means the heavy lifting, all the complex calculations, the data manipulation, the business logic, that all happens on the central application server.
Okay.
Which means the end user's PC, the client, can actually be less powerful.
Yeah.
It simplifies hardware costs, makes maintenance easier.
Right.
It centralizes software management, which makes updates way easier. And it guarantees everyone is running the exact same version of the software. No more compatibility nightmares.
Okay, that makes the distinction crystal clear. Centralizing the application logic just boosts efficiency and control.
Absolutely. And that brings us to the third type, the web server. Now, these devices specialize in communication efficiency, their main role, hosting websites and responding really, really efficiently to requests that come in from browsers, usually over the internet.
So when a big news site gets absolutely hammered with millions of requests during some breaking story, it's the web server army that's managing that spike. How does it cope with that huge concurrent load?
Yeah, it's all about speed and scale. Web servers are optimized to handle HTTP requests incredibly fast.
Okay.
And to manage those massive traffic events, like you mentioned, they're usually set up in clusters. They use techniques like load balance, which basically just distributes all those incoming requests across multiple physical servers, or sometimes virtual ones. It ensures the site stays up, stays available, and prevents any single point of failure from crashing the whole service.
Wow, that structural specialization is really powerful. Okay, so we've gone from the device literally on your desk to the engine room powering everything. Now let's pivot a bit. Let's look at how digital devices interact with the physical world, moving away from just processing data and more into capturing and experiencing things.
Good transition.
We'll kick off with entertainment systems category number 7. This covers high-powered stuff like gaming consoles, giving you those immersive digital games, and also, increasingly, smart TVs.
Right, and the significance of both of these architecturally is the sheer bandwidth they chew up.
Yeah. Streaming and downloads?
Exactly. Gaming consoles and smart TVs are deeply network dependent. They demand constant high-speed data flow for streaming video, for game updates, for downloading enormous game files. I mean, they're really driving the consumer push for faster home internet connections.
Sure.
And smart TVs specifically, they've fundamentally changed how we consume media, right? By integrating networking right into the TV itself, they've sort of sidelined traditional broadcast methods.
Yeah, absolutely. Okay, next up, digital cameras, both still and video. Simple function, translating light and motion into data. For still photos, we capture images maybe for quick snaps or, professional archives.
And here's where the technical detail in the sources gets really interesting, particularly about data load. The difference between common compressed formats like JPG or JPEG
Hmm.
and the uncompressed raw formats, things like DNG, NEF, CR2, ARW, the size difference is just staggering.
Okay, let's pause on that technical nugget. Why should you, our listener,
Mhm.
actually care about the difference between a JPEG and, say, a DNG file? What's the big deal?
Well, JPEG uses what's called lossy compression.
Lossy, meaning it loses something.
Exactly. It literally discards some image information to create a much smaller, network-friendly file, which is great for sharing quickly.
Okay.
But a raw file like DNG, it's uncompressed, it keeps all the data the camera sensor captured. The downside, a single raw file can easily be 10, 20, even 50 times larger than its JPEG version.
Wow, 50 times.
Yeah. So architecturally, this is a potential nightmare for data transfer and storage management. If one pro photographer shoots a dozen raw files, okay, that's manageable.
Right.
But imagine 1,000 cameras on a movie set generating petabytes of raw video footage. That creates this massive specialized challenge for the file servers and the network systems that have to store and move that huge amount of data.
That connects straight back to the demands on the server infrastructure we were just talking about.
Okay.
And similarly, video cameras capturing moving images, they're vital for real-time stuff like video conferencing. Again, demanding really low latency from our networks.
Absolutely. They're turning light and sound into this continuous stream of structured data packets that have to get delivered almost instantly. Which brings us neatly to Category 9, navigation systems.
Right. GPS systems. These rely on the Global Positioning System, GPS.
Yeah.
Which is, I mean, it's a foundational utility now, isn't it?
Yeah.
Using devices talking directly to satellites way up in orbit to figure out where you are.
Correct. The core function is just providing that real-time positioning data. Now, we mostly interact with it through apps on our phones or maybe the dashboard in our cars.
Yeah.
But their function relies on dedicated hardware inside those devices, capable of actually interpreting those faint satellite signals and this continuous, accurate location data. It's not just for finding the quickest route to the shops.
No.
No, it's fundamental to modern logistics, tracking assets globally, even synchronizing time accurately across international IT systems. It's a huge background utility.
That's a truly global reliance then. Okay, finally we get to the hidden infrastructure, the 10th category, the stuff that kind of binds everything together but often goes completely unseen. Let's start with the communication backbone itself.
Right. So beyond the devices we physically hold, we have the communication systems. Phones, obviously, for voice and video, including that critical low-latency voice-over IP, VoIP,
VoIP.
which relies entirely on data networks, not the old traditional phone lines. Email systems, messaging apps, they all fit here too.
But the real traffic director, the absolute linchpin for all this data flow, that's the router, isn't it?
Absolutely. Think of the router as the main sorting office for every single data packet flying around.
Okay.
Routers are these essential communication devices, and their job is to direct data traffic between different networks and between all the different categories of devices we've just talked about. They manage complex network layouts, ensure you can connect to the internet seamlessly, allow data exchange
So without them.
without robust routing. The entire ecosystem just collapses into chaos. Your mobile phone can't talk to the file server storing your photos. Your smart TV can't reach Netflix. Nothing works.
Got it. Critical piece. And this leads us nicely to the 10th and maybe the most pervasive category, embedded systems. These are the specialized digital brains built right into other machines using microcontrollers and sensors.
Yeah, this is probably the most rapidly growing part of the whole IT stack right now.
Ugh.
These systems are designed for very specific, often automated tasks. And the sources we looked at highlight some popular off-the-shelf microcontrollers like the little Raspberry Pi Pico or Arduino devices, which let engineers and even hobbyists build these very specific single-task devices pretty easily.
And within these embedded systems, sensors play a huge role, don't they? Detecting things in the environment, temperature, motion, pressure, maybe even chemical signatures.
Oh, massively important, yeah. In the consumer world, they automate our smart homes, right? Controlling lights, heating, security systems based on occupancy or time of day. But the really massive application, it's in industrial monitoring. Sensors are constantly checking the health and performance of critical infrastructure, in power grids, pipeline pressures, complex manufacturing machinery.
Trying to predict failures.
Exactly. Predicting failures, enhancing efficiency. And the sheer volume of data generated by thousands of these specialized sensors operating 24/7. It's just staggering.
And then connecting those specialized sensors to the network that gives us the Internet of Things, or IoT, right?
Yeah.
Letting all these little devices talk to each other and share data for even better automation.
Precisely. IoT is really the application layer sitting on top of embedded systems. It means your smart thermostat isn't just detecting the temperature in your room.
Right.
It's talking to a weather forecast service, probably hosted on a web server, comparing that data to your historical usage patterns, maybe managed by an application server, and then optimizing your heating schedule all by itself.
Right.
Or think about a wearable fitness tracker. It's using embedded sensors to monitor your heart rate, your steps, whatever, in real time.
Yeah.
And it's constantly securely passing that information up to a server cloud for analysis and storage.
Wow. Okay. We have genuinely mapped out the 10 pillars of IT infrastructure. We've gone from the personal computer managing, your spreadsheets, all the way to some invisible embedded sensor potentially managing a critical industrial process.
It's quite the journey.
Yeah. And the key takeaway, I think, for you listening is realizing that every single component, whether it's in that personal stack, the server stack, capturing stack, or embedded stack, every piece has a clear, specific, and pretty much non-redundant functional role within this larger interconnected system.
Absolutely. The power of being well-informed here isn't just about knowing the names of the devices like router or MFD. It's about understanding how their specific specialized functions fit together to create this incredibly complex but also surprisingly resilient ecosystem that we rely on every single day. And, if we connect this to the bigger picture, think about it. We spend most of our time staring at that personal productivity stack, our phones, our laptops. But those embedded systems, the ones we never see, they're often the ones quietly maintaining critical environments. They're monitoring industrial processes where maybe a mechanical failure could be genuinely catastrophic, could cost lives or millions of dollars.
Yeah.
So it raises this kind of important question, I think. What vital, maybe even life or death function is being performed right now by some tiny specialized sensor embedded in a massive hidden IT system, a system you never even knew existed?
Wow. That is definitely something for you to ponder and maybe explore next time you see some complex machine just working seemingly all on its own.